Right. So as I was saying, there's another application which is a theorem of Licorice and Wallace that says that if you take a link on a three-sphere and you do Dehn surgery on this link, you can get any close connected three manifold from that procedure. Okay. So this is just some motivation. Well, there is another theorem that really is the backbone of this, which is the celebrated theorem of Thurston, which says that if we take a compact three manifold with a torus boundary, which admits whose complement admits a finite volume hyperbolic structure, then there is a finite set of exceptional slopes such that for each slope away from this finite set, if you do Dehn filling along this slope, you get a manifold which is hyperbolic. So by a slope, we mean a simple closed curve. In fact, the homotopy class of such gives you a diffeomorphism class of a Dehn filling. Okay. So what is an algebraic analog of a Thurston's theorem? So in Thurston's theorem, we know that the fundamental group of the manifold is G. It has a boundary which is a torus, so its fundamental group is isomorphic to Z squared. What we're doing in the second step of the Dehn filling procedure, we're killing one of the generators, or it may not be a generator, just an element of infinite order in Z squared. And as a result, we're getting this quotient group, G mod the normal closure of N. And this is the fundamental group of this hyperbolic manifold. Okay. So in this context, what we know is that G is hyperbolic relative to Z squared, which is H. In particular, more generally, we can say that H is hyperbolically embedded in G. I won't define what this means, but for the purposes of this talk, one can just think about this as hyperbolic, as relative hyperbolicity. I think that suffices. So for everything I will say today, so one could say that a group theoretic Dehn filling is whenever you have a hyperbolically embedded subgroup, just think about G being hyperbolic relative to H, then you take a suitable N, which is normal in H, and form this quotient group, G mod the normal closure of N in G, and that we call the Dehn filling, group theoretic Dehn filling. So why is that interesting? Because you can do that for many classes of groups. But there's a theorem, an important theorem of Dahmani, Girodel, and Osin from 2017 that is quite similar in structure to the Thurston's theorem, says that if you have a hyperbolically embedded subgroup in G, then there exists this finite set F of elements in H which are not the identity, so such that if you take a normal subgroup in H which avoids this finite set, then the H mod N, which I'll call H bar, is hyperbolically embedded in G bar. And you can do the same thing in the context of relative hyperbolicity. If G is hyperbolic relative to H, then there exists such finite set so that as a result, G bar is hyperbolic relative to H bar. Okay, so we will say that this is the sort of algebraic analog of Thurston's theorem. Okay, so why is that interesting? Well, this has many applications. So one application, I'll mention some, and this is not an exhaustive list by any means, but a virtual Haken conjecture of Agol uses Dehn fillings. So the proof of virtual Haken's conjecture by Agol uses Dehn fillings. there's a theorem of Antolin, Coulon, Gandini, which proves Farrell-Jones conjecture for certain relatively hyperbolic groups where the peripherals are residually finite with extra conditions that uses Dehn fillings. Isomorphism problem for certain relatively hyperbolic groups by Dahmani and Girardel. This again uses residual finiteness of peripherals, again with extra conditions, and a construction of purely pseudo-anodes of normal subgroups in mapping class groups of surfaces, which is a result of Dahmani-Girardel OSIN from 2017. And I want to advertise two results. One is a consequence of what I'll mention today on L2 Betti numbers, which is verification of the Singer conjecture for certain Anderson-type Einstein manifolds. This is joint work with Bin Sun. And more recently, we verified Baum-Cohen's conjecture with coefficients for certain relatively hyperbolic groups. This is joint work with a colleague of mine, Shintaro Nishikawa, from this year. Okay, so hopefully this gives you an idea that Dehn fillings are interesting objects to consider. Now I want to talk about related property, which is called the Cohen-Linden property. So just in the same setting as group theoretic Dehn fillings, we have G, the ambient group, H is its subgroup, and N is a normal subgroup in H. And we say that this triple satisfies the Cohen-Linden property, or it's a Cohen-Linden triple, if the normal closure of N decomposes as a free product in a certain way, namely that you can find a transversal of this group H times the normal closure of N in G, such that if this normal closure is a free product of conjugates of N by elements in this transversal set. Is that clear? Now, very important results of Bin Sun from 2020 says that essentially Cohen-Linden property is a consequence of subgroup being hyperbolically embedded, meaning that if you have a subgroup H which is hyperbolically embedded in G, there exists a finite set F which minus the identity, a finite set F in H minus the identity. And if the normal subgroup avoids this set, then this triple is a Cohen-Linden triple. Okay. So why is it called Cohen-Linden triple? Is because Cohen and Linden were first to observe this property in the context when G is a free group and H is a maximal cyclic subgroup. And N can be any infinite subgroup of H. And then Edgeworth and Howie showed that if you have a free product of two locally indicable groups and H is a maximal virtually cyclic subgroup which is not in any of the vertex groups, then it satisfies the Cohen-Linden property. In the case when G is hyperbolic relative to H, this was already shown by Groves, Manning, and Sisto. And more recently, this property has been verified for some classical and cubical small cancellation presentations by the work of Macarena Arenas and Arenas and Duda from 2023-25. Where? No, it's just any group, discrete group. I mean, in these examples there will be, but what's that? Yeah. And definition doesn't assume final generation, no. No. Right, so I just copied the same definition for the codependent property, and I just want to mention sort of consequence of this. This is an earlier work of ours with Dehn, which is sort of more of sort of homological nature, I would say. So if you take any G bar module A, so it's just a, say ZG, so it's a module over the group ring of G bar. And I can just write down the cohomology of this group, the normal closure of N with coefficients in A. And I know by codependent property it's a free product, so I just substitute. I use the fact that it's a free product. I can write it as a product, which is just not saying much. But what actually is true is as G bar modules. So you have a G bar action on the left here, and then here. You can actually see that as a G bar module. This is nothing than the co-induction of this cohomology. So it's a co-induced co-induction of the cohomology of N. Why is that interesting? Is because we have, for any short exact sequence of groups, we have the Linden-Hochschild-Serre spectral sequence. So this is the kernel. The middle group is G bar. Sorry, the middle group is G. The quotient is G bar. And whenever you have that, you have the spectral sequence with the E2 term converging to the group in the middle, which is the cohomology of the group in the middle, which is this term here. Now, since we know that this cohomology is the co-induction, we can substitute and use Shapiro's lemma, and we get this spectral sequence. Okay. And this is nice because I just rewrote this spectral sequence here. Yes. 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 So N is the you can think about the relators, and H is the normalizers. Yeah. Yeah. Good. Yeah, H bar is the yeah. H bar, sorry, yeah, H bar is H. Should I write it somewhere? H bar, yeah. So we have this. I don't know, maybe notation is like that, and then you have, yeah, this is defined to be H, and then H N normal in H, which is like that. Oh, H bar, sorry. Yeah. Okay. Right. So this is a spectral sequence. It's interesting because it connects all the sort of players in the game. So we have H bar, G bar, G, and N, I guess. So they appear. What's crucial is that normal closure doesn't appear. And that allows us to make some conclusions. And one of them is this, what we call this algebraic excision. So there's an isomorphism between the relative cohomology of the pair G bar H bar and the pair GH, where A is the A is G bar module. Another thing that we can conclude from here is algebraic finiteness properties of G bar, because you see, whenever you have a pair of a group and a subgroup, you have log exact sequence in cohomology corresponding to that pair. And now you have the same thing for the two pairs, so G bar, H bar, and G and H. But then there's natural maps going from G bar, cohomology of G bar to G, cohomology of H bar to H. But then the third one is an isomorphism. Every third one is an isomorphism. And that is useful because it can give you it can give consequences to one of them is algebraic finiteness properties. Another one is Poincaré duality criteria. So if you know, I hope there's enough time. So the other is Poincaré duality criteria. I don't want to say too much about this, otherwise I'll run out of time. So maybe, or run out of battery. Yeah, all right. And more recently, we realized that we can actually use this result together with a theorem of Serre, very surprisingly, a theorem of Serre that tells us the structure of finite subgroups in G bar whenever we have a Cohen-Lindner property. So for instance, when you have a one relator group, you know where the finite subgroups come from. They come from whenever you have a relation which is a proper power. The same thing for in some classical small cancellation presentations. But in fact, all of these can be seen as a consequence of the Cohen-Lindner property and this nice theorem of Serre. Yeah, sure. Yeah, yes. Yeah, I'm not saying anything new, but if you go beyond those settings, you get something. You get new things. Yeah. Okay, so let's look at this algebraic excision again. So it has this result here. Now let's go back to the classical three-manifold setting, and let's see what we had. We had manifold M and its boundary here, and we filled it in with a solid torus, and we got a manifold which is closed. And classical excision says that you have this isomorphism in cohomology, right? You just take out the solid torus, and then this is just the excision axiom in topology. Now, algebraically, if you just replace, because all these spaces are spherical, what you get is, well, you have the cohomology of G bar, because that's just the fundamental group of this manifold, and then you have the fundamental group of this the solid torus, which is H bar, and then G and H. So classical excision gives this algebraic excision in this context, in this particular example. So then a former student of mine, Kevin Lee, saw this and said, well, is it true in general? Is it actually something that you can prove in general, that this property is an application of a topological excision coming from a particular space? and it turns out to be true. So let me give you the construction. So we have this Cohen-Linden triple, GHN. What you do is you have KG1 spaces. So BG is a classifying space for the group G. BH is a classifying space for the group H, subgroup H. By the universal properties, you have a map from BH to BG. And then because you have a map from H to H bar, which is the quotient map, you have a map from BH to BH bar. Then you can form their mapping cylinders. So there's a mapping cylinder of the map on the right. So this mapping cylinder of this map here, and this is a mapping cylinder of this map here. Then you see that they have a common top, so you glue them together. And this is actually what we want for our Dehn filling space. We call this a Dehn filling space for this triple. And it turns out to be a classifying space for Dehn filling quotient. Oh, sorry. Thank you for reminding me to show it. Right, so we take this space, this mapping cylinder, which is the mapping cylinder of this map, and this mapping cylinder here of this map, glue them along their common top, and we get the classifying space for Dehn filling quotients. Okay. Now, this algebraic excision you can see now is just a consequence of usual excision because I can excise this part here. So this is like the solid torus in a three-manifold setting. I can take it out and I get a manifold without with the boundary. Right. Okay. Skip the proof of that. So one thing you can give is actually geometric finiteness properties, not just algebraic ones. And the way you can do that is, so if you know that G is of type Fn, so meaning that it has a classifying space with finite and skeleton up to, finite and skeleton. And if you have subgroup H, which is hyperbolically embedded, then for all sufficiently deep normal subgroups in H, the Dehn filling quotient is of type Fn if and only if H bar is of type Fn. And you can just see that from just looking at this picture. So I think the interesting case is going from right to left. So assuming that H bar is of type Fn, what does that mean? That means that this part here has finite and skeleton. And we assume that G has finite and skeleton, so this part. Because H is hyperbolically embedded, it's a quasi-retract, and therefore, so that's a result of Dalman-Giraud-Delanosin, and that implies that H is of type Fn. So then we can find a B classifying space which has finite and skeleton. So this part has finite and skeleton. And so basically, we're gluing things which have finite and skeleton. As a result, we get a space with a finite and skeleton. I mean, this was a bit surprising to us because to get the algebraic finiteness properties, we had to use, in our previous work, the spectral sequence. So we had quite a complicated argument showing that from this spectral sequence, we would get this algebraic finiteness properties. But from here, you can just look at the picture, essentially. Yeah. So you have a yeah, that's a good point. So you need to have a Cohen-Linden property. And if you have a Cohen-Linden property, then this construction gives you classifying space for BG bar. So it means that Yeah, you can always do this picture, and you'll get that it has finite end skeleton, but it not it will only mean something if you take n sufficiently deep, because then it will be a classifying space for the Dehn filling subgroup.
Are you saying, or maybe I didn't understand, so you're saying that if n is sufficiently deep, then GHN is
Yeah. Yeah. And then this gives you a classifying, this space is a classifying space for BG bar. Okay. Right, thank you. Right, so what was the point? Another point here I wanted to make is that things which have finite end skeleton are nice from L2 Betti number point of view, because they allow us to, well, they're possible good spaces for computations of L2 Betti numbers. So we want to use this space to make such computations. So let me just quickly mention the definition, which is the algebraic approach that we take in our work. So L2 of G is the Hilbert space of square summable functions on C. The group von Neumann algebra is the subspace of the bounded linear operators on L2G on their left regular representation. And there's this von Neumann dimension on G, which is kind of a trace-like function from NG modules. So NG is a ring. We think about modules over this ring just purely algebraically. And this gives us a dimension function from, so every module over this group ring gives us a number from 0 and infinity, including 0 and infinity. And all we care about is really this nice properties that it has. So if M is finally generated NG module, then this dimension is finite. And it has this property that it's additive if you have a short exact sequence. Okay. Just to give an example, if the group is finite, then L2G is the same as the group binomial algebra, same as the group ring. And in that case, this dimension is really 1 over, remember doing this. So this dimension is really 1 over the order of G times the dimension of this vector space over C. Yeah. Now you can look at, you can form this chain complex, because the group ring sits naturally in this ring here, the von Neumann algebra, and you can do this tensor products. You take the chain complex of the CW complex, you tensor it over the group ring with the NG. You have this chain complex, and you take its homology, again, purely algebraically. And you call this homology of X with coefficients in the group binomial algebra. And you define its L2 Betti numbers as this dimension of this homology. You see, this homology now will be a module over the group ring, because it will still have an action of NG from the left. So we can talk about its dimension, and when in this context, it's exactly the L2 Betti numbers. So this is one way to define L2 Betti numbers, but it's the equivalent way of defining L2 Betti numbers. So this was for G within. This was with for G acting on a space X or CW complex X. So we define L2 Betti numbers of the group G as the dimension of this homology, where we replace X by EG, where EG is the universal cover of BG. So it has a free action of G. It has a nice CW model structure, and we can just define the L2 Betti numbers in this way. And you can extend this definition for the pair, you can define, if you have a CW pair with the gene action, this definition just extends naturally to the pair. Just going back to an example where we have a finite group, if you have a finite free GCW complex, then you can see that L2 Betti numbers are nothing more than ordinary Betti numbers divided by the order of G. Why is that? Well, just look at this case where I mentioned that when the group is finite, the dimension of V, von Neumann dimension, is the same as the ordinary dimension divided by the order, and you just now here the von Neumann the NG becomes just the complex group ring, and if you do these replacements here, you just get exactly this formula. Just follows immediately, right? Okay. Now there is a important conjecture, which is the Stronger-Thier conjecture, that says that for a finite type free GCW complex X, meaning that it has finite skeleton in each dimension, then the L2 Betti numbers are in this additive subgroup of Q, where you're allowed to divide by the orders of the finite subgroups appearing in G. So this represents the orders, all possible orders of finite subgroups appearing in G. Okay. Well, this is a proof by example. You can see this is true when the order is finite and we have this situation. Okay. Right. So our main result is the following theorem, and I will unpack it, but let me just say first, let me just read what it says. Let G be a virtually compact cubical group that's hyperbolic relative to abelian subgroup H. Then there exists a finite index subgroup K normal in H, such that for every sufficiently deep normal subgroup N in H, which is contained in K, and K mod N is torsion-free, then L2 Betti numbers of the Dehn filling quotient are the same as the L2 Betti numbers of G. So virtually tough property means that you have a finite index subgroup that has this property. So G has a finite index subgroup, which is compact cubical group, meaning that it's a fundamental group of a compact non-positively curved cube complex. And we really need these conditions. We can't avoid K because we use mononormal special quotient theorem, and the theorem is false if you don't assume that K mod N is torsion-free. So they are not just, well, one condition is we need, the other condition is we also need. Okay, so let me just say how the steps in the proof, and then I will mention applications, and then if there's time, I'll mention how it works. So in the first step, what we want to do is we want to relate L2 Betti numbers of G bar, H bar, this space with an action of G bar, and this space with an action of H bar. So notice that G bar is, well, it's here, it's G mod the normal closure that acts on EG mod the normal closure, right? And H bar is H mod N, so it acts on EH mod N, right? So we have these L2 Betti numbers, and in the first step, what we're going to do is we're going to get an inequality between these L2 Betti numbers, certain inequality. In the second step, we're going to approximate these L to Betti numbers of these spaces by L to Betti numbers of G and H, respectively. And that's going to use Luke's approximation conjecture, or at least the case where we know it's true. And now from step 1 and step 2, what we get is an inequality that relates L to Betti numbers of G, H, G bar, H bar. And the nice thing is that our H we started with was abelian. So their L to Betti numbers of H and H bar will vanish. And we'll just get an approximation of G bar, L to Betti numbers of G bar and G. Okay. And in the third step, we need to use the Strong-Latier conjecture for the case we know it holds, which is in our setting and the setting of the theorem, to argue that no matter what the Dehn filling, I will always be in this additive subgroup. We can arrange it to be this additive subgroup of Q. Now, that's a discrete range for these L to Betti numbers. And because we can, by step 1 and 2, we argue that they can be arbitrarily close, this will imply that they in fact have to be equal. Yes.
So this holds.
Yes.
And so for this, you're like, so you're using that H is abelian, or just that H is amenable?
I think for we have a more general statement where we have to assume that G is virtually locally indicable, and H is hyperbolically embedded, amenable subgroup. Yeah, some extra conditions. Yeah, there's a more general statement, but yeah, just first one steps, it's not necessary to say that it's just virtually abelian. Yeah.
So you probably are using the Marilyn type equation from dimensional approach. It's residually finite to use the approximation.
We use, yeah, I'll come to that. We use theorem of Hakim Zaperan and Alvarez Lopez, which they verified the Luke's approximation conjecture for virtually locally indicable groups.
Yeah, right. Are you using approximation?
More general. No, not finite index. No. It comes later when we need to use a TS conjecture. I mean, yeah. So maybe it's more clear when I come. Yeah, I haven't used it. No. This was just supposed to be like a warm up to the actual proof sketch. But sorry, yeah. But yeah. So I maybe I'll answer those questions. Yeah, when we get around to it. So let me just mention applications. There are 4 I think we have in our paper. One is the single conjecture for Einstein, certain Einstein manifolds, the spherical Einstein manifolds. Upper bounds on deficiency of Dehn filling quotients, virtual fibering criteria for Dehn filling quotients, and some examples of hyperbolic groups with exotic subgroups. And I want to mention the last 2 because sort of they go hand in hand. So virtual fibering. So a theorem of Fisher-Killock. I think I said it. I wanted to say it this way because it was done by David in case where n equals 1, and then more generally by Sam. So that GB virtually refers of type FPK over the ring Q. Then L to Betti numbers of G vanish up to degree k if and only if there's a finite index subgroup G prime in G, which surjects onto Z, such that the kernel is of type FPK over Q. So for instance, when K is 1, FP1 means the group is finally generated. And we're saying that the group, when the first delta Betti number vanishes, then the group virtually surjects onto Z, where the kernel is finally generated. Okay. So as a corollary of our theorem and this theorem, we have that let be just in the same assumptions as in the theorem, virtually compact cubical group, hyperbolic relative to abelian subgroup H. Then for sufficiently deep normal subgroup n, as in the main theorem, satisfying there's this K and where K mod n is torsion free. Then you have that G bar virtually fibrous if and only if G virtually fibrous. Okay, so to prove it's just straightforward. Well, first, G being virtually compact cubical group like this implies it's of type F infinity. And this picture argument that I showed earlier shows that G bar is also of type F infinity for deep enough n. So we know G and G bar are of type F infinity. They satisfy the assumptions of the theorem of Fisher-Killock. So we know that G virtually fibrous if and only if delta Betti numbers vanish up to this degree. Now, by our main result, we know that delta Betti numbers of this vanish if and only if they vanish because they're equal. And then we can just know that the same thing for G bar. This virtually fibrous if and only if its delta Betti number vanish, again by this theorem, because G bar satisfies the assumptions of this theorem. And then we just get the conclusion that, oh, sorry, did I state? So this, yeah, so from these two we get this. This is what I wanted. No, sorry, from this equivalences we get that this virtually fibrous if and only if this virtually fibrous. That's what I wanted to say. I can't look, I can't. My logic doesn't work diagonally. Sorry. Right. Okay. What about exotic subgroups in hyperbolic groups? Well, there was this very important question that was open for a long time that said that is every subgroup of type F in a hyperbolic group hyperbolic? And this was disproved by Italiano, Martelli, Magliorini in 2021. If G is a fundamental group of Dehn filling space of cost hyperbolic fab manifold, which fibers over a circle, so it's a fundamental group of a four-dimensional pseudo manifold, and it's of type F. The subgroup H is of type F, but is not hyperbolic. That was their result. And as we recently know that there's another reason to care about these groups. So that was very nice. Another question that was, again, well known of Noel Brady that said that for n greater or equal to 3, is there a hyperbolic group G which has a subgroup H which is of type Fn but not of type Fn plus 1? And this was unknown until 2022, where Sandrich and Pai showed that certain hyperbolic arithmetical lattice in projective unitary group N1 has finite index subgroup which surjects onto Z, with kernel of type Fn, but not of type Fn plus 1. Okay, so what is our contribution? So our contribution is sort of the algebraic version of these results. You take a cost arithmetic hyperbolic n manifold, then there are infinitely many hyperbolic Dehn-Fielding quotients of its fundamental group, such that if the dimension is even greater than 4, then it virtually fibers up to degree the middle degree middle degree minus 1, but not the middle degree, so FPK. And if the dimension of this manifold is odd, greater or equal to 5, then it virtually fibers where the kernel is not hyperbolic. So you get on both cases you get subgroups. So this group is hyperbolic. You get a subgroup which appears as this kernel, and it's not hyperbolic because it doesn't satisfy higher finiteness properties, and this is not hyperbolic for other reasons. For the sake of time, I think let me just skip the proof of this result. Let me just the last 5 minutes or so go deeper into the proof of this. Well, at least this sort of the sketch of the main theorem. So how do we relate L2 numbers of G bar, H bar, and these G spaces? You consider the Dehn-Fielding space. You look at its universal cover. So think about these pieces. They will lift into certain equivariant spaces. And you take homology of these with NG coefficients. What you get with applying so what you get is you get a long exact sequence here and a long exact sequence here. Oh, long exact sequence here. Maybe I should just stand here. Sorry. So I'm not tempted to go near the computer. So you have a long exact sequence here and long exact sequence here, and this is the excision here. And I'm just conveniently replaced G H with G bar H bar. So notice that if I apply my dimension function, this will give me the L2 numbers of G bar. This will give me L2 numbers of H bar. This will give me L2 numbers of the pair. And here I will have L2 numbers of the other terms that I wanted to compute or relate. So because L2 numbers of, so H was a billion, the L2 numbers of H bar will vanish. So what I get is L2 numbers of these are the same as the L2 numbers of these, which are the same as this. So this L2 numbers of these are the same as L2 numbers here. Now I can truncate this long exact sequence into pieces. The right side truncation will give me this inequality. The left side truncation will give me this inequality. So that's the step one. So we related the L2 numbers that we wanted to relate. Now we want to approximate this one with G and this one with H. And this is where we apply Luke's approximation conjecture. It says that if we have an inverse system of normal subgroups in G over the directed set I, such that the intersection is trivial, then whenever you have a GCW complex of finite type, L2 numbers of this complex, G complex, are the same as this limit. Okay. Now, Luke's approximation theorem is a consequence of this conjecture. Well, you can see it as a consequence. Why? Because these, when you have a residually finite group where we have this nested sequence of normal subgroups, these L2 Betti numbers really become ordinary Betti numbers divided by the orders of these finite groups, which are the indices of the normal subgroups in G. And there's a theorem of Hawkins, Zapper, and Lopez Alvarez that says that Luke's approximation conjecture is true for virtually local indicable groups in more generally, not just for directed over directed set, but in the space of marked groups. And so I'm just speeding up, sorry, because I'm out of time. So what we observed is that their theorem has a nice corollary, and it's that if you have a violently generated virtually local indicable group, and you have a free GCW complex of type FPK plus 1, there exists a finite set that in G minus the identity, and if normal subgroup avoids this finite set, then the L2 Betti numbers of this space G space and this quotient space with the G mod n action are very close. You can make them arbitrarily close. Now, that applied directly to what our situation says, that we can approximate L2 Betti numbers of these guys by L2 Betti numbers of G, and these guys by H, which we know is abelian, therefore it's 0. And then if you look at the sequence, these things drop out. Sorry, these things drop out, and these things become close to G. So this is L2 Betti numbers of G minus delta, L2 Betti numbers of G plus delta. So what we get by steps 1, we get this. So it's like, Shakespearean play where all the players kill each other and the only main 2 characters left, and they're like dueling it out, right? So the remaining question is this one. Yeah, I'm really proud of that, by the way. And so I'm going to keep it there for a little bit. So I'm really, yeah, just give me 1 more minute to finish. No, I'll finish. Yeah, I'll finish soon. So what is the final step? The final step is, okay, we're getting close, but are we close enough? So that, so to speak. So step 3, we know that we have a virtually compact special group. So a virtually compact cubical group, we take G1, which is finite index, and exactly that. By a theorem of Groves and Manning, if we assume that also K mod n is Z, is isomorphic to Z, let's make that assumption, then G bar is virtually compact special. In which case, there's a theorem of Shreve that says that whenever you have a virtually compact special group, it satisfies the Tia conjecture. So therefore, this Dehn filling quotient, its L2 Betti numbers are in the range we want, because it satisfies L2 Betti numbers. Now, what is true is that more generally, we want K mod n to be not just Z, but we want it to be some free abelian group. And we had to work a bit more to show that we can actually, when we have that, we can take further quotients, really take further quotients of our group, get to the situation where this K mod Z is free, is Z, show that it satisfies the AT conjecture, and use this theorem of approximation theorem of Hawkins, Zapper, and Lopez Alvarez to say something about our original situation where K mod n is Z to the M. And that showed that the L2 Betti numbers are, yeah, so that finishes step 3 and shows that they're equal. Thank you. Right. So if you try to generalize Thurston's theorem to higher dimensions, it doesn't work because if you do the Dehn filling, you still get higher rank abelian groups because you're just killing one z in z to the n. So what you do is what Anderson showed is that you get Einstein manifolds. So these manifolds for large enough Dehn fillings, these manifolds support an Einstein metric. So like the Ricci curvature is proportional to the curvature tensor, and that's known as the Einstein. That means that the manifold supports an Einstein metric, and for us, it was just an observation that you can do this Dehn filling, and you see that these manifolds have the same L2 Beatty numbers as the L2 Beatty numbers of the manifold you started with. And we knew that the L2 Beatty numbers of the manifolds we started with satisfy the Singer conjecture. So these manifolds do as well.